Welcome back. Up to this point in our Kubernetes Network Policy series, we have covered basic isolation within a single namespace. But real-world production environments don't live in a single namespace. In a true microservices architecture, you have a three-tier application structure: a front-end handling client request, a middleware handling business logic, and a backend managing database or persistent storage, each running in its own dedicated namespace. In today's video, we are stepping up our game. We're going to cover two critical real-world network policy scenarios. One is allowing cross-namespace traffic from front-end to middleware, and setting up bi-directional traffic between front-end and middleware. By the end of this video, you'll know exactly how to write airtight namespaceSelector and podSelector rules to build a secure multi-tenant network mesh in Kubernetes. Let's jump straight in. Allowing traffic from front-end to middleware namespace. Your front-end pod needs to make an API call to a service running in the middleware namespace. With the default deny network policies enforced, that connection gets dropped like a hot potato. To fix this, we need to apply Ingress policy on the middleware pods that explicitly trust incoming connections from pods residing in the front-end namespace. Let me draw your attention to a few super important lines in this manifest. Notice where this policy is applied. So, network policies are namespaced resources. This policy lives inside the middleware namespace because it controls Ingress entering the middleware. And podSelector.match labels. So we're targeting pods labeled on middleware inside this namespace. The Ingress.from class, look closely here. We combine both namespaceSelector and podSelector. NamespaceSelector looks for the namespace labeled, which is basically the front end, and podSelector ensures that only pods labeled run equals web app is allowed. Notice how the namespaceSelector and podSelector are items in the same array element under the from field. This creates an logical AND condition. If you placed them under separate dashes, it would create an logical OR condition, opening up traffic from any pod in front-end namespace or any pod named web app in any namespace. So always double check your rules. A small typo could result in an entirely undesired network configuration. Now let's go ahead and apply this network policy to allow traffic from the front-end namespace to the middleware namespace. Right, the policy is applied. Now let's run a quick test to make sure everything works. Wait a minute, so it's still failing. Why can't these pods communicate? So to better understand what's happening under the hood or behind the scenes, I have created this visual representation of this cluster. The yellow lines indicates the communication path between the pods, and pay attention to the arrow that indicates the direction of the traffic. Now imagine a set of virtual doors that are placed inside and outside of these namespaces. All these doors are currently closed, depicting the state of the cluster when the baseline default deny policies is enforced. By applying this allow ingress from middleware to front-end policy, we have essentially opened only this door. Now, remember the default deny policy that is still in force for all the namespace? That's still blocking the web app pod in the front-end namespace to be able to reach the middleware pod in the middleware namespace. For this communication to happen, we need to be explicit in our policy to say allow egress from front-end to middleware. Therefore, we need to apply another policy in the front-end namespace to virtually open this closed door. Let's apply this policy now and validate the results. Let me run the connection test, and it worked as expected. Did you notice that the connection is only unidirectional? Why did the web app to middleware work, but the middleware to web app failed? This is one of the most common points of confusion when learning Kubernetes network policies. So let me break down what just happened under the hood. Let me bring up the visual representation that helps with the reasoning why it behaved that way. When web app initiates a request to the middleware, two specific doors must be unlocked. That's what we have proved and is working fine. First, the inbound door or the ingress policy that defines the middleware namespace needs an ingress rule saying middleware pods are allowed to accept traffic coming from the frontend namespace. And the other one is the outbound door or egress policy that defines the frontend namespace needs an egress rule saying web app is allowed to send traffic out to the middleware namespace. But stateful return traffic is not the same thing as initiating a new connection. When middleware tries to start a new request to web app, the rules reset. First, the middleware hits its own namespace firewall because our default deny egress policy is active and we have not given middleware an egress rule to reach the frontend. The packet gets dropped immediately right at the source. Secondly, even if the middleware could send the packets, the frontend namespace has a default deny ingress policy with no ingress rules accepting new requests from middleware. So remember this golden rule. Stateful connection tracking allows response data to flow back from an existing request. It does not grant permission for the destination pod to start a brand new connection in the opposite direction. If you do want the middleware to be able to initiate new connections to web app, you'll need to configure an explicit bi-directional policies, which is exactly what we are going to build in our next chapter.